In 1934, a dump truck rolled off a factory floor in Cleveland, Ohio, and the men who built it had no idea what they had just started. The Euclid 1R could haul 15 tons of rock. 15 tons. At the time, that number seemed almost absurd, because a standard highway dump truck could barely manage 5. But here's the thing about mining. 15 tons wasn't enough. It was never going to be enough. Because the deeper humans dug into the earth, the more material they needed to move, and the economics of extraction demanded one thing above all else: bigger. Today, the largest mining trucks on the planet can carry 450 tons in a single load. Their tires stand 13 feet tall and weigh 12,000 pounds each. Their engines produce 4,000 horsepower, and they cost more than most houses you'll ever walk into. A single tire replacement runs $42,000. Not the truck itself. The Caterpillar 797F lists at $5.5 million before you add a single option. These machines are too heavy to drive on any public road ever built. They would crack asphalt like dried mud under their weight. So they exist in a parallel world, crawling up and down haul roads carved into open pit mines that stretch for miles. A world where the vehicles are too large for human infrastructure, purpose-built for holes in the ground that can be seen from orbit. This is the story of how dump trucks grew from 15 tons to 450 tons in less than a century, and why, despite everything, they're still getting bigger. To understand why mining trucks had to become their own species of vehicle, you need to understand what regular trucks face when they enter a mine. Picture a copper mine, not the postcard version, but the real thing. An open pit mine is essentially a wound in the earth, a spiral of terraced roads descending thousands of feet into rock. The grade on those haul roads can hit 10% or more. That doesn't sound like much until you realize a fully loaded truck is fighting gravity with every inch of ascent, hauling dead weight that would crush anything designed for a highway. Standard commercial trucks were designed for paved highways where the maximum legal weight in the United States is 80,000 pounds. About 40 tons. The entire truck and its cargo combined. Now imagine asking that same truck to climb a 10% grade with 100 tons of ore in the bed, on a road surface that might be loose gravel, wet clay, or dust 6 inches deep. The transmission would cook itself within hours, the brakes would fade before you reached the top of the first climb. And the frame would twist under loads it was never engineered to handle. And that's assuming the tires didn't simply shred themselves against rocks the size of watermelons. Mining companies learned this the expensive way. In the early 20th century, they tried using fleets of smaller trucks. Dozens of them, running constant loops from the pit floor to the processing plant. The math seemed simple enough. More trucks, more capacity. But the math lied. More trucks meant more drivers. More drivers meant more labor costs, more training, more human error. More trucks on the haul road meant more traffic, more dust, more accidents. The road itself degraded faster under constant traffic, and every single one of those trucks had to be maintained, fueled, and eventually replaced. Parts for 20 trucks cost more than parts for 10 trucks. Now the arithmetic of volume crushed them. The industry came to a brutal realization that still drives decisions today. If you want to move more rock, you don't add more trucks. You build a bigger truck. R.G. Letourneau was a man who thought about problems differently than everyone around him. In the 1940s, while other engineers were trying to squeeze more power out of conventional drivetrains, Letourneau asked a question that seemed almost naive. What if the wheels themselves were the engines? He developed something called electric wheel drive. The concept was elegantly simple once you heard it. Instead of routing power through a transmission, a drive shaft, and axles, you put an electric motor inside each wheel hub. The diesel engine on the truck doesn't drive the wheels directly, it drives a generator. The generator produces electricity. The electricity flows to the motors in the wheels. Stop and think about that for a second. No transmission, no drive shaft, no differential. Just wires running to motors the size of barrels, one inside each rear wheel. The mechanical complexity that destroyed conventional trucks in mining conditions simply vanished from the design. A transmission that has to shift under 200 tons of load will eventually fail. Every gear change stresses components that were never meant to carry that kind of torque. An electric motor that simply spins faster or slower based on current has far fewer ways to break. There are no gear teeth to strip, no clutch plates to burn, just copper windings and magnetic fields doing the work that used to require an entire drivetrain. Letourneau's electric wheel drive became the foundation for nearly every ultra-class haul truck built since. Look under any 400-ton mining truck today, and you'll find his basic architecture still running, refined over decades, but fundamentally unchanged. He solved a problem so thoroughly that no one has found a better answer. But even Letourneau couldn't have predicted how far the concept would be pushed. The 1960s and 70s became a kind of arms race. Mining companies wanted bigger trucks. Manufacturers competed to build them. Each new model represented a bet on the future of extraction. In 1963, the W. Abco 3200 arrived with a 100-ton capacity. A decade earlier, that number would have seemed like science fiction. Now it was just the baseline, the new floor beneath which no serious mining operation would consider. Then came the Terex Titan. In 1974, General Motors rolled out a truck so massive it held the world record for the next 2 decades. The Terex Titan could haul 350 tons. Its empty weight was 260 tons. It stood 3 stories tall, and when it rolled past, the ground trembled under equipment that had never existed before. Only one was ever built. The economics didn't quite work at the time. Mines weren't yet deep enough or large enough to justify machines of that scale. The Titan was a proof of concept, a statement of what engineering could achieve when budget constraints were lifted. It proved that the technology was possible. The question was simply when the industry would catch up. That Titan still exists. It sits on display in Sparwood, British Columbia, a monument to ambition that outpaced its moment. Visitors stand next to its wheels, and their brains struggle to process the scale. The tire comes up to the shoulder of an average adult. The bed could hold a modest house, and the industry did catch up. By the 1990s, open pit mines had expanded dramatically. Copper, iron ore, coal, and gold operations were moving billions of tons of material per year. The demand for larger trucks didn't just grow, it accelerated. In 2004, Liebherr introduced the T282B, the first diesel-electric truck to reach 400 tons capacity. The machine weighed over 200 tons empty. Its bed could swallow a 2-story building, and it represented a fundamental shift in how mining companies thought about extraction. Here's the calculation that drives everything. The cost per ton of material moved. Every dollar a mining company spends goes toward that number. Equipment, fuel, labor, maintenance. All of it divides into the total tonnage hauled. A 400-ton truck requires roughly the same number of drivers, mechanics, and support staff as a 200-ton truck. But it moves twice the rock. The cost per ton drops. Profit margins widen. The mine stays competitive in a global commodities market where a single percentage point can mean the difference between profit and loss. In copper mining, that margin pressure is everything. The difference between a mine that runs and a mine that closes might be a few cents per pound. That pressure, the relentless mathematics of extraction, explains why trucks kept growing even after they seemed impossibly large. In 2013, the Belarusian manufacturer Bel AZ unveiled the 75710, 450 tons, the current record holder. This machine burns roughly 100 gallons of diesel fuel per hour at full load, 100 gallons in an hour. Its 2 engines together produce over 4,600 horsepower. Each tire costs more than a new car, and when fully loaded, it weighs over 1,000 tons, pressing down on 6 tires with a force that would liquefy ordinary pavement. And still, engineers are designing even larger trucks. The mathematics haven't stopped demanding it. Let's talk about the tires, because they represent one of the most underappreciated engineering challenges in the entire mining industry. A tire on a Cat 797F stands 13 feet tall, taller than most ceilings, taller than the basketball player who could dunk without jumping. It weighs approximately 12,000 pounds empty, and it has to support over 100 tons of load on a single contact patch while climbing grades, navigating turns, and absorbing impacts from rocks that would puncture anything found on a highway. Manufacturing these tires is closer to building a bridge than vulcanizing rubber. Layers of steel cables, synthetic fabrics, and specialized rubber compounds are bonded together under pressures and temperatures that would vaporize an ordinary tire. The process takes weeks. A single flaw in the casing, invisible to the eye, can cause a catastrophic blowout when the tire is carrying 200 tons up a 10% grade. The rubber itself is engineered to resist cuts from sharp rocks, heat buildup from continuous operation, and the flexing that occurs with every rotation. At 35 miles per hour, which is fast for a haul truck, a 13-foot tire completes roughly 150 revolutions per minute. Every rotation flexes the sidewall. Every flex generates heat. Manage that heat poorly, and the tire cooks itself from the inside. The lifespan of a mining tire is 12 to 18 months under ideal conditions. That means a truck running 3 shifts per day might go through a set of 6 tires every year. At $42,000 per tire, that's $250,000 annually just on rubber. And that's assuming nothing goes wrong. Tire failures don't just cost money, they cost time. When a tire blows at the bottom of an open pit mine, that truck isn't moving until a service crew can reach it with a crane capable of lifting 12,000 pounds. In some mines, that crane might be an hour away. Every hour that truck sits idle, the mine loses tonnage. Multiply that by the cost per ton of material, and a single blowout can represent losses in the six figures. This is why tire monitoring has become its own discipline. Sensors track internal pressure, temperature, and tread wear in real time. Algorithms predict failure before it happens. Because in a pit mine, an unexpected blowout isn't just inconvenient. It can shut down the entire haul road behind it, stranding half a dozen trucks carrying hundreds of millions of dollars worth of capacity. Now, about those haul roads. You cannot drive a 1,000-ton vehicle on any surface built for human transportation. The pressure per square inch would destroy asphalt in hours. Concrete would crack and heave. Even hardened military runways designed for bombers wouldn't survive a week of loaded haul trucks. So mining companies build their own roads, engineered specifically for these machines. The construction starts with compacted subgrade, often dozens of feet deep. Layers of crushed rock are added and rolled until the surface can support concentrated loads that would liquefy ordinary soil. The road surface itself is usually gravel, specifically graded and watered to control dust. Water trucks run constantly, spraying thousands of gallons per shift to keep particulates down. In dry climates, that water consumption can rival a small town's. In some mines, the haul roads are treated with binding agents that create a semi-permanent crust, reducing both dust and maintenance. Maintaining these roads is a full-time job for entire crews. Graders smooth the surface daily, sometimes multiple times per shift. Engineers monitor grade and drainage to prevent pooling that would soften the roadbed. A single neglected pothole can damage a tire worth $42,000. However, a section of a road that develops ruts can slow the entire fleet, adding minutes to every cycle and tons to the opportunity cost. Some mines have taken road engineering even further. Trolley assist systems, the same concept that powers electric buses in cities, have been installed on the steepest haul road climbs. Overhead wires provide direct electricity to the truck's motors, supplementing the diesel-electric system. The truck essentially becomes a train, drawing power from the grid rather than burning fuel. The economics make sense on the longest, steepest climbs. A truck pulling 400 tons up a 10% grade for 2 miles burns diesel at a rate that would make a ship captain wince. Connect that same truck to overhead power and the fuel consumption drops dramatically. The motors run cooler, the engine works less. But trolley systems require infrastructure, poles, wires, substations. The capital cost is enormous, and the system only works on specific road segments. For most haul operations, the trucks remain purely diesel-electric, their engines running continuously from the first shift to the last. The trucks will never leave their mines. They're manufactured on-site or delivered in pieces and assembled at the mine mouth. Most will run their entire service life within a few square miles of Earth, crawling the same spiral roads until their frames crack or their economics become obsolete. The latest evolution in mining trucks isn't about size. It's about removing the human entirely. Caterpillar and Komatsu both operate autonomous haul trucks in mines around the world. These machines drive themselves. No cab, no steering wheel. No operator wondering if they should have taken that bathroom break before the last load. Just sensors, GPS, and software that calculates the optimal path from loading point to dump zone. The business case is straightforward. A human driver needs breaks. They work in shifts of 8 or 12 hours. They make errors, they get tired, and tired operators make decisions that damage equipment or cause accidents. They call in sick, they quit, they need training, and that training takes months before a new operator is fully productive. An autonomous truck doesn't get tired. It runs 24 hours a day with breaks only for fueling and maintenance. It follows the same path every time, which reduces tire wear and road damage. It brakes consistently, which reduces brake pad consumption. And it never exceeds speed limits or takes corners too fast, shaving years off the life of the chassis. The early autonomous deployments were experimental. Isolated trucks in controlled environments, monitored by teams of engineers ready to intervene if the software hiccuped. But by the 2000s, entire fleets were operating without human operators on board. Rio Tinto runs more than 130 autonomous Komatsu trucks in its Pilbara iron ore operations in Western Australia. BHP has followed with their own autonomous fleets. So has Fortescue. These aren't experiments anymore. They're the new baseline for certain types of mining operations. The technology relies on differential GPS accurate to a few centimeters, radar and LiDAR systems that detect obstacles, and communication networks that coordinate multiple trucks simultaneously. The control room might be hundreds of miles away, then staffed by technicians who monitor the fleet on screens but never touch a steering wheel. They intervene only when something unexpected appears, something the software can't handle on its own. There are problems, of course. Autonomous systems struggle with unexpected obstacles, things that weren't in the map. A boulder that rolled onto the haul road overnight, a piece of equipment parked where it shouldn't be. Weather can degrade sensor performance. Heavy rain, dust storms, even just low sun angle can confuse cameras and LiDAR. And software updates have to be managed carefully, because a bug in the navigation code could send a 400-ton truck off the edge of a bench with no one at the wheel to correct the mistake. But the trajectory is clear. The largest trucks ever built are becoming the first trucks to drive themselves. Walter and the human operators who once sat 3 stories above the pit floor, hands on the wheel, are watching from a control room miles away, managing machines that no longer need them to move. Here's what stays with you after you've stood next to one of these trucks. The scale doesn't register immediately. Your brain doesn't have a reference point. You look at a tire that's taller than a basketball hoop, taller than the doorway you walked through this morning, and some part of your visual processing refuses to accept it. Then the engine starts, and you feel it in your chest before you hear it. The vibration travels through the ground, through your feet, through your skeleton. 4,000 horsepower isn't just loud, it's physical. It's a presence that occupies the space around you. And these machines exist because humans decided to dig holes in the earth that are visible from space. The Bingham Canyon copper mine in Utah is nearly a mile deep. The Grasberg mine in Indonesia has moved more than 6 billion tons of rock since operations began. The material extracted from these wounds in the planet becomes the copper in your phone, the iron in your car, the rare earth elements in the battery that powers whatever device you're using right now. To move that much material, you need trucks that don't fit on any road designed for humans. You need tires that cost more than cars and last barely a year. You need electric motors inside wheels because conventional drivetrains can't survive the load. You need roads built like runways and maintained like operating rooms. You need algorithms that can drive 1,000-ton machines up and down grades that would challenge a mountain goat. And eventually, you need to remove the human from the cab because the machine has grown beyond what a single operator can safely control, and the economics demand that it run around the clock without rest. The 15-ton Euclid 1R from 1934 wasn't just a bigger dump truck. It was the first step down a path that led, inevitably, to vehicles the size of houses, carrying loads measured in hundreds of tons, driven by software through artificial canyons carved into the crust of the planet. They'll keep getting bigger, they always do, because somewhere, right now, an engineer is looking at a spreadsheet and the math is telling them that the cost per ton can still come down. All they need is a bigger truck. Not all they've ever needed is a bigger truck. And that truck, whatever it looks like, whatever records it breaks, will one day seem quaint compared to what comes next. The Earth isn't getting any smaller, the demand for what's beneath it isn't going away, and the machines we send into the ground will keep growing until they reach whatever limit physics finally imposes. No one has found that limit yet.